In this lecture, we're going to discuss leveling. Leveling is survey measurement in one direction, vertical. A couple things about leveling. Like I said, it's one dimension. We capturing difference in elevation and perhaps calculating elevations on points. We don't concern ourselves with where they are horizontally. We assume that the surface we're working on is flat. Just like in construction layout, we're going to assume the surface is flat. In fact, it's not. It's a level surface is curved. So some terminology. A benchmark is a permanent point of known elevation. That's usually primary control. It could perhaps be a DOT or a National Geodetic Survey established benchmark. In that case, it's probably got a published data sheet of some kind at the agency that established it, and that's how control was brought into a lot of sites in the past. Was they would find a benchmark of suitable datum and quality, and they would run that elevation onto their site. And of course now we use GPS for a lot of control. Temporary benchmarks, it's a point of known elevation. It's just not something that has the permanence of a benchmark. It's not something that you put a lot of effort into establishing. So it just might be control on the site. It could be a rim on a manhole or top of a platform or a step, something like that. So a turning point, when you run levels, these are even just points that you have to set. It's like a traverse point. It's not something that is going to last forever. In fact, these are even worse than traverse points because you're probably not going to ever revisit them, because when you run control for elevation, like traversing, I mean, a lot of it's not even on the site. So, but you need to be able to see between the back site and the foresight to level. So turning point is just going to be something that you put the rod on so that the instrument person can read the rod. Backsights, looking back at a point of known elevation, such as a benchmark or turning point. And a foresight is looking ahead to establish an elevation. When I run levels, I don't carry elevations. I just take the backsights and foresights and book them in that manner. I wait until I'm done, and then we'll do some calculations to see how well we closed, and then after an adjustment, then you populate the elevations in the book. Perhaps people that carry elevations, that's fine. Do whatever your boss wants you to. It's his business, it's his license. I just don't carry elevations only because I don't like there to be confusion between adjusted elevations and elevations from the original unadjusted level run. Height of instrument, it's the elevation of the line of sight of the telescope. That's the horizontal plane of the center cross here in the reticle. Balancing of sites is something that we do to reduce and eliminate some errors that are inherent in this process. If you don't balance your sites, then you have to do some error analysis and then correct for these errors. Closed loop is beginning at one point and ending at the same point. And closure is the difference between the beginning and the ending elevations. It doesn't have to be a closed loop. You could run between two benchmarks and start with A and close on B and see the difference between the elevation that you established on it and its posted elevation. So the level surface. The level surface is curved. We live on the earth, and if you were to put two survey rods up 1,000 feet apart, it may be negligible, but there's a error that's creeped in there that may have to be considered depending upon the precision of the work you're attempting to do. So the level line is curved. We assume locally that it's flat on a construction site. There's a datum. That's something we'll talk about a little later. That's the reference plane that you're using. It could be anything. We'll look at datum planes a little later, but so every elevation is connected to a datum. It could be an established datum nationally, it could be a local datum, or it could be an assumed datum. But somewhere there's a zero. This is the type of level, dumpy level, that was used for years by surveyors. Not much in use today. They do still serve a purpose sometimes. They aren't subject to some of the issues you might have with a modern automatic level. I've used them in the last several years a couple times, only because they fit the need of the job. This is a automatic level. This is the workhorse of most survey shops. They simple to use. They have, it's all you need really, but there's automatic levels like this one. This picture is an optical, I would call it an optical one. There's digital levels. They're all digital. Most digital levels and most automatic levels share the same pendulum compensator. The digital level is just a camera. So with this automatic level, you would look through the telescope to read the rod that and you're going to read the rod height. The parts is an eyepiece with that's where you'll look through and you see the reticle, that's the crosshairs in the eyepiece. That's where you're going to focus the eyepiece to get the crosshairs sharp, and also you are going to, as you adjust the reticle, you'll be changing the focus so that you find that point where the crosshairs are sharp and you can read the rod clearly. Everybody's different. Wear glasses. One of the first guys I worked for basically said, these instruments are just eyeglasses that everybody can wear, because you focus it to read what you want to read. So you're going to focus on the rod using the excuse me, the focusing adjustment, while you make sure that the reticle is clear so you can read the crosshairs. So there's a gun sight for rough sighting. The 90-degree mirror allows you to set it up and not have to be on your tiptoes to look over the bullseye bubble. And these sit on a they have the same 5/8 by 11 thread in the bottom, and they have 3 leveling screws like a tri-brack. The only difference is this doesn't detach. It's one piece when you take it out of the instrument case. And this is a digital level. It's an automatic level with a camera. It simplifies some of the work in that it has some automatic checks built in. It would read the rod on the right, the barcode. That's the camera part. It's going to read the barcode, and it's going to determine the height of the rod reading, and it's going to determine the distance to the rod. But like a lot of electronic equipment, it has electronic level bubbles, tilt check. The big advantage that I like is that it will record the observations onto a data collector or SD card. They're all different. This is a Topcon, and it looks like an old Kia model, like an SDL 30. I used to have one of those, and didn't have memory. We had to hook it up to the data collector or book it. If you bought one today, it almost certainly has internal memory. And you don't rock a barcode rod. You use a rod level to plumb the rod, and you'll see what I'm talking about in a few minutes. But you can also look through excuse me, a digital level and read the rod on the left. It's just the barcode rods have a normal rod on one side and barcode on the other. Excuse me. And you can get Invar rods and fiberglass rods and all sorts of different rods for these digital levels. Just be careful, because one manufacturer may not read another manufacturer's rod. Surprise, huh? And this is the automatic level compensator. You've got a little prism hanging from a couple pieces of film, not unlike Mylar. And as the level changes, it's going to not twist, but direct that horizontal plane such that it stays level, because those are prisms on the right and left of it, and as it goes out of level, or perhaps wasn't leveled properly, to an extent, it will correct with those prisms and the hanging compensator, because it's free floating, and as the instrument might go out of level, it will compensate to a certain point, and that doesn't mean you shouldn't be keeping an eye on it, but there's a little bit of wiggle room in there for you. Sometimes with these compensator levels, you have to treat them right. I mean, you can't bounce them around, but sometimes if you tap the tripod, make sure it's swinging. You can tap the housing of the level gently, but if you think it's hung up and it's not reading properly, then you might try to tap it. These are just some accessories that go with leveling. A turtle is basically allowing you to have a nice point to turn the rod on. The rods we use have a flat bottom, and if you were going to rock the rod, you don't necessarily, you're not staying flush with the surface. With the knob on a turtle, you can do that. You can do the same with a leveling pin. A little more convenient to carry. If you need a good place to turn, you just jam that into the ground, and it's good enough for a turning point, because turning points aren't something that you're going to want to recover in the future. Rod level is just what it sounds like. It goes up against the rod, and it allows you to plumb the rod. A lot of rods have rod levels attached, and not a fan. I had bought a set of rods, and it turned out you couldn't adjust it very well. So the hand level, that's handy in the way that if you're doing a lot of work on hills, you can see, if you put the hand level up, the hand level is going to give you level, of course. You will see if you'll be able to view the rod through the instrument at that height. So you might move up or down on a slope to where you can read the rod for the back sight, and then set the instrument up, instead of setting the instrument up and then realizing you can't see the rod because you're below it. And just like the level rod, you can't use these with digital levels, but most of us will have a 6-foot wooden rule in our back pocket or our vest, or a 25-foot tape. And sometimes in a pinch, you can read these. You're up on forms and somebody needs to take a shot. You can use a wooden rule or tape. It's not something I would carry levels with, but if you're trying to quick check something, it's graduated in the same manner. So when you're looking through a level, you'll have crosshairs, and you'll see an upper, a middle, and a lower. The middle crosshair is the one that you're going to read for the elevation reading, the height of target, or any number of terms. The upper and lower will be used to establish the distance to the rod. So it says this image says multiplication factor of 100. So that's the stadia constant. Most instruments have a stadia constant attached to them, and it's if you had a rod out at 100 feet, you would read 1 foot from the bottom hair to the upper hair, and then you would multiply it by the stadia constant to get 100 feet. That's how that works. Most instruments have a stadia constant of 100. Some European instruments don't, because they were built for the metric system. But so reading a level rod, this is a typical fiberglass rod that most people have, and you can see it's graduated in hundredths of a foot, which is the unit we work in, feet in hundredths, and you would read it directly. The bottom reading is 7.08, so the distance between the black lines, the white areas, is 100th, and same with the distance between the white areas, the black is 100th. So you would read the middle wire for leveling. And if you didn't have a rod level with you, you can rock the rod. It's an old trick. And you're going to read the lowest reading on the rod, because that will be plumb. You can run levels with the middle wire, a single wire, or you can run 3-wire levels where you would read the bottom, middle, and top wire. 3-wire levels have a lot of advantages. If you're running levels that have to conform to a specification, you need to know the distances, the backside and foresight distances. So when you do 3-wire leveling, you record the bottom, middle, and top wire, and you average the top and bottom wire, and it should match the middle wire. It's a good check. So as you're doing your run, you're not making a mistake. And like I mentioned, the difference between the top and bottom wire times 100 will give you a distance for a instrument with a stadia constant of 100. And specifications have usually some kind of a formula for you to see if you conform to it. And this one is E would be the distance of the level run, the sum of the backside and foresight distances times some number that they've decided on, and then that product will give you a number, and if it meets the spec, then you're good. If not, you're back out running levels. So single run levels can be run through a benchmark you want to set. If you just go from benchmark A, which is known, and set B and call it a day, you have no way to know if you made a mistake. You read a lot of rod readings, you wrote them down, and did something creep in there. Did the rod man put the rod down, light up a cigarette, and put the rod back in the wrong spot, and now it's a 1/10 higher or 2/10 higher? These things happen. So when you run levels, you want to have a way of ensuring that the benchmark you set is correct. And that way there, if you started with benchmark A, which was NAVD 88, and you ran it through benchmark B and said, oh, here's your elevation in 88, and there's a bust on your run, you're not going to know it because you haven't done anything. There's no redundancy. You haven't verified it. So you can either run it through to another benchmark of known elevation, or you do a closed loop. You could run from A to B and then back to A. The caveat is you have to break the setup. When you establish, use the instrument to establish B, and now you want to return back to A, just break the setup, set it up again, cite B, and then return to A. If you don't break the setup, there's no redundancy, there's no check on that rod reading that you use to establish B. And this is a double, and they call it a double run level circuit. So you go from A to B, establish B, run back to A. You should start and end at the same value for A. So in the mathematics of leveling, it's addition and subtraction. There's two equations to remember. So the elevation is the height above your datum. It could be NAVD 88, NGV 29, could be assumed. You'll see later there's all sorts of datums out there. So when you set the instrument up and you're going to backsite a known elevation, you're going to be determining the height of the horizontal plane of the middle crosshair in the telescope. So you're going to read the rod, and that rod reading will be added to the elevation, and that's going to be your height of instrument. Then you're going to turn the level physically. You don't pick it up and move it. You're going to turn it physically because you've determined its height of instrument. Now you read the rod on the foresight, and the elevation of the foresight will be the elevation of the height of instrument minus the rod reading. So it's benchmark plus backsight equals HI. HI minus rod reading equals elevation. Those are the two equations to learn in leveling. So whenever even if you're setting out stakes, it's HI minus rod reading gives you the elevation. So here we have a backsight of 521, elevation of 925.23 for our benchmark. So our HI is 930.44. To our foresight of 9.05. We subtract that from our elevation of our instrument, the HI, and we're going to get 921.39. Leveling in a nutshell. Granted, you have to be on the right point, you have to be plumb, the instrument has to be set up, it has to be leveled. You have to take all the personal errors out. If you're booking it, you have to write down what you read correctly, things like that, but that's just common sense. So this is just a simple setup. You can make these tables. I've got notes later. You'll make these tables in your book or on the SD card, the digital level, and backsight is plus, HI, foresight minus, elevation, and a description. We always have to describe what it is we're doing. So in this case, we're starting with a benchmark 7088. I think that was a Mass DOT benchmark I was using, and give it a datum in the book so that somebody who comes in after you will know what it's referenced to, because otherwise it's just a number. And datums they aren't far apart. I mean, 2988, they're within 3/4 of a foot or less in some places. So it's difficult to tell them apart. So you have to give that metadata. You have to put in the book what you're doing so that it's understood. We have to be very clear with our notes. So in this case, you can see we started benchmark 7088 and set up, and then we turn the instrument to turning point 1, read that rod, we move the instrument from where it is to the next setup, and we backsighted turning point 1, we foresighted turning point 2, move the instrument beyond turning point 2, we sight turning point 2, foresight turning point 3, and it just goes on and on. So this is 3-wire leveling. And as I mentioned, you're going to use the distances. This was notes out of the Sakia level, which had no memory in it. So that's why we didn't get the wire readings. We just got the distance in the display. It was HT and distance was what it was set up to display. So it read 4.65 as a rod reading, and it displayed the distance as 152. And so we calculated our HIs, foresights. Again, it read the rod, it gave us a distance, and we just carried these elevations. The distances, sometimes with the digital level, you could shoot the rod but not save it. So if you're trying to conform to a standard, let's say we'll look at a standard later, third order, maybe you can't be out of balance by more than 10%, say. So you would shoot the rod, and if it wasn't, you would move the rod band back and forth to where he needed to be to conform with the standard. However, now this can you see the bottom of the rod? There's other parts of standards that we'll look at a little later, but so that's one of the advantages of the digital level. You can shoot your distances. If you were running it with an optical level, an automatic optical level, you just pace them out, and you'd have to read them. And then if you had to move the rod band back and forth, you did. It just took a lot longer. Sometimes you need to establish the elevation of the ceiling. You could be in a tunnel, and they want to know what the elevation of that ceiling is. So you invert the rod and put it on the ceiling, and you read it directly in the instrument. It's going to be upside down, so you just have to be careful that you're reading it correctly. But in your notes, you'll note that it's inverted by putting a negative sign in front of the reading, and that tells people that was the elevation of something above the horizontal plane of the level. Otherwise, the mathematics isn't going to work. If you just put in 8.45 and you say HI minus foresight, you're going to get an elevation below the plane of the instrument. So if you put a negative in front of it and just say HI minus a negative foresight, you're in fact adding, so you'll get a elevation above the height of instrument. Now, there's something called an intermediate foresight, which this is what usually an inverted shot will be. It's difficult to use the surface above you as a turning point. So you can see from the first setup on the left in this image, they shot a back sight of 6.23 and determined the elevation of the instrument, the height of instrument, 106.23. And they shot the ceiling as a negative 8.45 and have 114.68 for the elevation of the ceiling. And then right below it, they have a shot on turning point 6, which is 4.89, and you can see in the image that you go from HI to foresight and then elevation. So you could have 15, 20, 30 of these intermediate foresights, but they aren't part of carrying the elevation in the level run. The turning point is, when you read 4.89 on the turning point, you subtracted it from the HI to get an elevation. Now you move to the setup on the right, and you read turning point 6 as a back sight at 2.54. Your HI is 103.88. So generally, when you have intermediate foresights, they would be booked before the sight on the turning point, because as soon as you shoot a turning point, you want to move the instrument so that the rod person is right there, and all they have to do is turn the rod to the new setup. And at the new setup on the right, they shot the ceiling again because there was a change in elevation, and again it's a negative, and HI minus a minus is a plus. And then they would shoot turning point 7 last after all the intermediate foresights, and this would just continue on. You know, this could be a tunnel, it could be any number of things. Maybe, you know, it's a concrete floor and they're concerned about it shifting, or any number of pipes, you know, drainage, maybe you're shooting some pipes, any number of reasons. But, you know, you invert the rod, you put it on the point, and just be sure you indicate in the book it's a negative because it's inverted. So these are leveling notes, and notes are as individual sometimes as the people taking them. But whatever format your company uses, it's whatever they want. So in this case, it was the engineering department I worked for, a lot of highway work, so we had a lot of the, it was defined by station and offset. So we always had station and offset on the left, and then on the other page we had room for a description. So we have typical notes plus HI minus elevation. This is single wires. And we kept track of station, backside, height of instrument, foresight, elevation, and then there's a column here for elevation after adjustment. They carried elevations on this run. Again, however the gentleman, lady you work for who has the license will dictate how the work is done. And if they carry elevations, great, do it. If you're doing a double run circuit and you do it properly, you break the setup after you establish the end and then read the end before you start back to the original point, you should come back to the same elevation. So that means that if you added up all your back sights or the plus readings and you add up all the foresights or the minus readings, they should equal each other, because in whatever direction up or down you went, you came back to the same spot. So all the downs and all the ups should add up and equal each other. That's a quick check a lot of guys will do in the field because you're not carrying elevations. You don't need to. You just do a page check, and then you're done. If you got a good check between your sums of your backsights and foresights, your elevations will be fine, because it's all derived from the backsight and foresight rod readings. Whoops. 3-wire notes. Again, backsight distance, HI, foresight, and then foresight distance, elevation, point number. The notes have changed over the years. This was done with the LS15. It's a digital level from Leica, and they assign points to all elevation shots, and the guys keep track of it in the book. I worked for a public office, so everything we did was a public record, and it was available to the public. So we would book our level runs in addition to capturing it electronically. So if there was somebody who wanted to use our work, they were welcome to it. You can see he's made a note there, NAVD 88. That's the datum we were working on, and the elevation was in meters. There was two things: NGS, a lot of DOTs, a lot of control work is done in meters, and then they convert it to international feet or US feet, depending upon NGS, whatever state it might be in that they've established the work. So I'll talk about this more a little later, but you just have to know the metadata of your data. So this is NAVD 88, and the elevation posted was in meters, and I don't work in meters. I was in Massachusetts. It was a U.S. foot state, so I used the appropriate conversion to get into feet, and then we were off to the races. In the very top of the page, you can see it says peg test. Anytime my guys would run levels, they would peg the level. It takes about 4 minutes to peg a level, and I'll show you a peg test later on at the end. But a peg test will ensure that the level is functioning properly, that there's no issues with it. I mean, if you run levels all day and you come back and hit where you started and you don't get the right elevation, did you make a mistake? Is the level not working? If the level's not working, that was an easy thing to discover through a peg test. So, yeah, that's on you. But, again, you work for whoever you work for. If their policy is something else, whatever, do it. It's not a big deal to me. I'm just here to impart this information to you. A peg test ensures what you're doing is correct, and it's not a big, it's not going to kill a lot of time. It's just very simple thing to do. So in the leveling notes, like I said before, you want to put enough information in there that people can get back and figure out how this stuff was established and where it came from and what datum it's on. So you can see there's a couple references in this book. One is to book 500, page 95. Another is to book 149, page 78. And he's saying, call this number 100. I don't know what that's all about, but if you were going to use this information later on, then you might want to look at this. There's no datum called for here. It's 1987, so I don't think 88 was established yet, so it's all 29. Or is it? It could be an assumed datum, But we look at the information, and Book 149 established it, and it's right there, checked within 400 from TBM 2071. So there's a book that was compiled with all sorts of benchmarks, and during the Depression, the WPA had people just working to keep them working, and so they established a lot of elevations at that time in the 30s, and they published these books, and the benchmarks are control based on NGS standards, first order, second order, third order. TBMs, you're going to find, were established where they needed to be. A lot of water pump stations had TBMs attached to them during that time. But this one says new chisel square on new bridge, checks within 400ths of 2071. So you go look up 2071 and you'll find out, obviously, it's 29. Not obviously, but probably. And then the other node is book 500, page 95. So here on this page, he's giving you a location of it. It's an old railroad bed on South Main Street. It's Cohasset. Now we could see that in the other page. And then there's the location of the chisel square. He's described it. Corner concrete abutment on southeast corner of bridge. So if you need to go out and look for this, there's a description on its location and you can find it. Never have enough information. So we looked at the level surface. It's assumed to be a horizontal plane. Okay. It's not, though. As you can see, the level surface is above, the line of sight is above the level surface. And the level surface is bending to conform to the shape of the Earth. Gravity, it's pulling it down. So the effect of gravity is the same across the Earth. So if you have light or any kind of emitted ray like that, it's gonna bend down parallel to the Earth, because gravity is the same here, 100 feet away, 1,000 feet away. So it's always going to be below the horizontal line of sight of a properly adjusted level. If the level's out of adjustment, anything's possible. It's garbage. So this bending of the line of sight there's two things going on here. There's curvature, which is the curvature of the Earth, and refraction. So curvature, a curved level line, causes the rod to be read too high due to horizontal instrument level line, and the line of sight passing through the atmosphere to bend below the horizontal instrument line is refraction. So the level surface is below the horizontal of the instrument, and refraction is below the horizontal of the instrument. So most of the time they combine these errors, and they can calculate them based on the distance from the instrument, that object that is being observed, the prism pole. These apply equally to total stations. There's a setting on your total station that there's maybe 2 or 3 selections you can make for K, which is what they call this sometimes, K factor. And because they're both, they just combine them. And if you're working within a certain distance, the instrument applies a factor. If you're working beyond that distance, to another distance, so there might be 2 or 3 ranges of distances that the instrument can apply, but it only applies one at a time in the instrument. It may ask you to select it. So there's errors introduced by these, and then you use the correction to correct for them. They're there. You can't do a lot of it sometimes in the field, but there are some personal errors you can certainly reduce or eliminate. That's the idea. You correct blunders, you model the systematic errors, and you adjust the random errors. You'll never know what the random errors are, but because of probability, you should be okay. Systematic errors, there's you model for those. There's a formula that tells you the temperature and pressure affects the instrument this way, and you model for that based on the conditions the instrument is in at the time of measurement. And then blunders are just mistakes, and they can be personal mistakes, they can be any number of things, but you can't have those. You can't adjust out blunders or systematic errors, because then what you've done is you've introduced those into your adjustment, and the results are wrong because those errors, the blunders shouldn't have happened, and the systematic errors should have been modeled for and corrected. Incorrect leveling of the instrument, not paying attention, letting it go out of level and not paying attention. When it's settling, sometimes it's just a poor choice of a setup. You gotta get out of the sun maybe if it's a really bad hot day. There's parallax, which is the crosshairs and the level rod. If they're not both clear and in focus, you're not reading the correct height of target. So some of these rods we use have multiple sections, and if they're not extended fully and someone's reading that section, then they're not reading the correct height. But you can't see that through the instrument. You might see a couple feet of the rod, but you can't see if the rod is fully extended and it's snapped in correctly. The markings on the rod are clear. They're weared off and flaking, and it's difficult to see. Might be time for a new rod. Is he on the correct location? Like I said, did he stop, light up a cigarette, and talk on the phone while you were moving the instrument, and then you tell him to plumb the rod, he picks it up and he's still talking on the phone and he puts it in the wrong spot. So that's an error that certainly shouldn't have happened. Reading the rod incorrectly. Sometimes, I say you're far away. sometimes when you're closer, you can't see the foot markings on the rod. You might not have one of those in your reticle. And you just ask the rod man to move his finger up and down the rod to where he is on level, and he'll tell you what foot that is. Incorrect crosshair, if you read the top here. There's all sorts of reticles for instruments. Every manufacturer, there are all sorts of crazy reticles out there. So you have to make sure you're reading the correct one for the purpose you intend. And rod knot plumb. You can't tell looking at the face of a rod if it's plumb or not. You can, if he rocks it, puts a rod level on it, he can make sure it's level. But so those are errors that you have to eliminate from the work, or it won't be a happy day. So mathematical errors, if you complete the page check, double check the arithmetic, make sure it's all there. Pegging the instrument, you make sure it's working properly within calibration. And balancing back sights and foresights. If you've got unbalanced sights, then the error isn't equally distributed between back sight and foresight. Now you have to make some mathematical corrections to the data, which is unpleasant sometimes. Again, so if you're balancing your sight, distance 1 and distance 2 are equal, then you're eliminating the errors. You're eliminating the need to correct for the errors. Errors are always there. It's just by balancing your sight, you've balanced them out such that they have no effect on the readings. I keep adding this to a lot of my presentations now, only because NGS is coming out with a new datum. It's going to do away with the US foot. But in the past, they established all their elevations in meters, and then they converted them to feet. But they used US feet for the conversion. I misspoke earlier. They only used US feet for conversion. So if your state was an international foot state and NGS established an elevation in your state, they used the US foot conversion. So in the future, you realize that's a US foot, and you'd have to go back to meters and then convert to whatever the new conversion factors are, or if they're going to use the same for the international foot. I haven't seen any numbers, so I'm not sure. But just remember that every elevation they ever established was in US feet. And there's the link right here. If you go to this, there's a frequently asked question. This is just a copy of it. But with datum 23, you might have to go from US feet to meters and then to international feet, or if they're going to define it in some other way. Just be aware of that. That's that whole tirade again. So just realize that this is out of the Mass Highway Survey Manual. It was done in '96 during this metrification craze that went on. It lasted about 3 days. It was a disaster. Contractors wanted no part of it. I must have bought $2,000 worth of metric equipment, rods, prism poles, tapes, wood rules, everything. We weren't going to convert anything. Mass Highway wanted us in metric, and we just bought metric tools, and lasted about 3 years, and then they just gave up. Because it turned out contractors were just paying extra money to their surveyors to put it back into feet, and nothing converted. 15-inch pipe, they had no idea what they were talking about. They had hard conversions and soft conversions, and it was a disaster. It just they just threw their hands up. The surveyors could handle it. Smart people, but the contractors just didn't want to be bothered. So it went nowhere. But they spent a lot of money. The metrification guide, and they wrote all of these manuals in metric, and they still haven't changed the survey manual. This is still the current survey manual. It's still in metric. But they had to change everything else because the suppliers, when they talk about drainage pipes and frames for catch basins and stuff, it got out of hand. So the unit of length then was the meter, and all they're saying here is that it was the meter, and they used the U.S. survey foot to convert. And that's because in Mass there's legislation that dictates that. Chapter 97, the general laws, dictates that you use the meter to U.S. foot conversion factor. It's not a big deal on a construction site perhaps, but if you were doing geodetic work, you start to introduce some real problems into the coordinates that you're working with. So just be aware that the conversions are different for U.S. foot, international foot, and all the NGS elevations were determined using the U.S. foot conversion factor. Vertical datums. There's all sorts of datums out there. The two national ones are 29 and 88. 29 was called sea level for a long time. If you're looking at something, you see sea level, that's what 29 was originally called, and then they changed it because they determined that sea level on the East Coast wasn't really the same as sea level on the West Coast. Surprise. So they changed it to NGVD 29. And you'll have to work within whatever datum. There's 1,000 towns out there that never changed from 29 because as they built out their sewer networks, and it's all 29, the plans, and it's just a number, so who cares? Just keep it in 29. So that when people start tying into sewers and things like that, drainage, they can stay on 29. It's not a big deal. It's just you have to know what datum you're expected to be working on and find the appropriate control. So Mass Highway publishes this guide of relation of datum planes. It's in meters, of course. And you can see that, there's all of these datums out there because towns started laying out sewers. I worked for a company that was established in 1868, 69 or something. And so, he did a lot of sewer work, Worthington, and every town just kind of had their own datum because their water system, their sewer system. So as he did things in the 20s and 30s, it was all built out to those elevations, so they kept them. The other thing is, as you look at this, you see there's at the bottom, there's the MBTA, the Mass Bay Transportation Authority, Mass Water Resources. They got these datums that are 32 meters below what was originally sea level. Why would they do that? Well, it's because they have tunnels and they want to work in positive elevations. So they have an assumed datum, and you'd go into the MBTA and say, we're working for you and we need some control, and they'll give it to you. Mass Water Resources, again, big drainage works. Army Corps of Engineers, the Third Harbor Tunnel, they want to keep everything positive. So they've got these assumed datums that are well below 32 meters is like, what, 100 feet? So that gives them all that room to stay in positive numbers because it's just one less error introduced into the problem. So they don't have to worry about what was the sign of, now this tunnel's below mean sea level, so it's a negative 22, and if somebody misses it just led to more headaches than it's worth. So they just assume datums are fine, and they just stayed on these systems, especially anybody that has below ground works. But if you're working in those towns, you would go to the town and get control to be on that datum. And then you would list it in the field book, like we saw earlier. This is 88, related to all of the different assumed datums. So what's a benchmark? We talked about it earlier. So survey mark, benchmark, they're not the same. Benchmark is a vertical control. It's any number of physical things. If you do deformation studies, you're going to have a lot of benchmarks. You're going to establish a lot of control on buildings, and they're just single elevation only. They'll be tied into the building, but for what when you're just running through and hitting in a deformation study, you're just hitting these previously established benchmarks with elevations to see if they're settling or rising. A lot of times things are in 3D. That's fine, but when we're leveling, it's vertical only. Again, it says permanent benchmark, geodetic control intended to last decades, TBMs, short-lived. There are also tidal benchmarks that are tied into the tide cycle, I think 18.5 years, 18.6 years tide cycle. And sometimes you have to be on those tidal benchmarks because somebody wants a ship to go under a bridge at high tide. So you need to be able to say, this is your clearance at high tide. If you built a bridge and people can't travel under it except at certain times, once or twice a day, depending upon if you have 2 cycle tides or not, it can be a problem. Or you just hit the bridge. So tidal benchmarks are a little different. They reference to a tidal datum. mean sea level, mean lower lower, mean higher higher. There's a whole gang of them. It's kind of a specialized thing. And there's a relation to the geodetic datums, because I mean, GPS is not going to give you tidal datum. It's going to give you ellipsoid height, and you're going to convert it to something. And the data collectors will do 88, straightforward, state plane coordinates, straightforward. It's not going to do tidal datums because they're apt to change over the time. So be very careful if you're working on the water, and you need to do something. I did one project was a walkway to a barrier island, and we couldn't have the walkway covered at high tide, so we had to make sure it was above high tide, at high tide, so people could walk out and enjoy what was there was a beach there. And so just be careful. Let's see. So these are kind of different kinds of physically monumented points. There's a disc and an outcrop of ledge, stainless steel rod driven to refusal. Those are a bunch of companies make them. Bernstein makes them, and it's very stable. You drive that rod into refusal, or to where you just so many pounds per minute on the driving machine. I don't call that anymore. And then you affix a finned insert. You slide it over the stainless steel rod. It's like 3 or 4 feet long. It's full of grease, and as the ground heaves and settles, it grabs that finned insert, and that's what slides up and down, and the rod is left alone. I have a bunch of those set, and you just come back and they're fine. A lot of work, kind of expensive, but if that's what the client wants. And then sea stability is going to be a disc or a bolt, a rivet, who knows, poured in a placed concrete post, and maybe a bound. If your chief's not too bright, you have to be careful, because some of these they aren't very stable. So this is a benchmark sheet from NGS. You go online and you say, I need vertical control. What you want to be sure of, you can go in and say, I need, there'll be a million of these, but if you're doing leveling, you want to look for something that says the orthometric height was determined by differential leveling. Okay, that's truly leveled control. Okay, so up here, whoops, where am I? Oh, right here, ortho. Readjust it. So look at this and make sure if that's what whoever you're working for, whatever they want. But if you're looking for vertical control that was tied to a datum by leveling, you have to see this, because it could say it was determined by GPS observation. That's not really, that may not fit the specification. You have to read it. And if it was determined by differential leveling, it's got to have no vertical order, because vertical orders are based on for NGS anyways, right now we're based on a procedural, length of run, misclosure, things like that. There is none of that with GPS. It's you get what you get based on whatever satellites are overhead. So this is where you'd see the vertical order, and this is the statement you want to look for leveling. And then don't forget, everything's got a geoid height, and they post dynamic heights now, which means it's moving. We don't move much up here, but here's your ortho height. This is the NAVD 88 orthometric height determined. Orthometric height was determined by differential leveling. That's what you're looking for. So there are leveling standards. This is an out-of-date one in Mass. Mass has a goal standard now, GOAL, where you have to do whatever you design the survey to meet the criteria of the client. But in the past, this is a typical. So level loop shall close to a minimum accuracy of 0.05 feet times the square root of the length of the level run in miles. So you can't meet a specification like this without running levels and capturing the distance of the back sites and foresights. You can't run single level and meet this. It's kind of outdated anyways, but it's still, if that's the spec, that's the spec. So when I had my guys running levels, digital level, automatic optical level, we just kind of conform to these third order levels from the FGCS, Federal Geodetic, I don't know, committee standards. I don't know. There's other parts of third order levels when you start talking that I didn't conform to, and I would make a note on the plan of the survey report that we did third order levels, except we didn't do the meteorology. We didn't keep track of the temperature, the relative humidity, or something like that. And as you get into these second orders, firsts, and things like that, that's part of the information you have to collect. But for highway work, topos, things like that, at a small scale, this would allow me to sleep at night, warm fuzzy feeling, and it yielded good results. We never had any trouble if we followed these rules. We had metal and wood rods. Level bubble on the rod? No, we used a rod level. It's easier to adjust if it goes out. Solid turning points, turtles, 9 pounds. There are a bunch of turtles out there. That one I showed you isn't 9 pounds. But I think Hickson makes one that is NGS compatible. So, maximum feet sight, 295 or 590 per setup. Because the further you go out, you start to have trouble with curvature and refraction. This is a good happy median for a lot of these, a lot of this work. So we wouldn't read below. It says 1.64. When you start reading below 1.5 feet on a rod, the lower you go, you're going to start to have, in the hot weather, heat shimmers, thicker atmosphere. So it's more difficult to read the rod. Least count of the instrument is 1 millimeter. One piece rod recommended, not required. We never used that. Single wire, no, we did 3. Collimation error, not a problem. Peg test every 2 weeks, no. Every time we took a level out of the case, we pegged it to make sure it was working. Repeatability, 1 second of arc. Some of these things are the instruments specifications, and some of them are procedural requirements. But those, we followed those, and always had good levels. Never had any trouble with elevations. The digital levels are amazing. I mean, just the Sakia, we bought that like 15 years ago. I think it was first generation, and it just was wonderful. They had really lousy rods. They were awful. Kept breaking. Cost a fortune. Nowadays they have really good sturdy rods, and you can get the Invar rods if you're doing crazy levels for somebody. I had a set of those at the county. It's a lot of work and running levels with Invar rods, but you can do it. It's not a big deal. So we talked about the peg test and knowing if your instrument is working properly. So I'm just going to walk you through a little exercise in a peg test. So it's test the accuracy, and what you do is you're going to set up the instrument, equal distances, and you're going to read both rods, A and B. And then you take the instrument and you move it and you unbalance the setup. So you're going to exaggerate the error in these readings. And a properly adjusted instrument will read correctly. One that's out of adjustment will not read correctly because you're exaggerating the setup and the distances. Did I skip a page? Yeah, sorry. So on the first setup, you're going to read the rods and the distances. And because it's balanced, it should, these are good readings. And then you're going to unbalance it. And like you can see here on the bottom one, you move to, I like to go outside. Some guys will move close to A, but in between A and B. Your call, whatever. That's how it's set up a lot of times. I just understood it better having the rod at P, and I could see both errors because the line of sight is going through A to B. So if the line of sight is declined or inclined, it's the same on both. It just made more sense this way to me. So anyways, you've got your rod readings and your distances, and if your instrument's in good working order, the difference in elevations should be equal because you're looking at two rods, and the difference in elevation between them should be the rod readings you just made. So if AB doesn't equal CD, then you're out of adjustment. And so if you're out of adjustment, it's because something's wrong, but it's the second setup that you're going to work with those numbers because those are the ones that need to be adjusted. So CD is called the false difference in elevation, and the inclination error of the line of sight and the net difference is going to be equal to the difference between the two setups. So you can see the true difference in elevation is the balanced sights, balanced distances. And the false is going to be the unbalanced readings. So again, we proportion the error, and you can work with the fire rod. And you're going to calculate out what the error on the fire rod is. So there's our error in the fire rod. Okay, so it's proportionate. So we took the distances and we multiplied it by the difference in the rod readings. And there's our error, negative 0.0143. So the correct rod reading, you're going to add it, subtract it algebraically from the line of sight. So the true rod reading at the far rod should have been 7.161. So if the error is negative, the line of sight is declined. And if it's positive, the line of sight is inclined. And if you want to know the error per 100 feet, you just divide the distance from the instrument to the far rod, the 230, by 100, and you'd have 600ths per 100. And that's something you need to know. That's how the misadjustment would be. That's how you can compare an instrument to instrument to a specification. They standardize it this way in so many hundredths per 100. Now, you can check it by doing the near rod at A. And it's the same. You just rearrange the equation for A, and you should get an error. I mislabeled some of this stuff. That should say near rod. So here's the error at A. So your corrected rod reading is going to be the rod reading, the correction, and there's your corrected rod reading. So now you have a corrected rod reading at B, a corrected rod reading at A, and you subtract the difference, the elevations to get the difference, and it should match the true difference in elevation you read with the balance setup AB. And it does. So if you want to check to see if you calculated the error properly, that's how you would do it. That's all for leveling. We're going to talk about stakes and grading at the same time. So I didn't get into how you label stakes if you're setting out stakes. We'll talk about that when we get to grading.